Hello everyone, welcome to lecture 16 on Mechanics and Materials 1. In this lecture we begin with the topic bending. We have 4 lectures on the topic bending and this is the first one in our lecture series on this topic. Today we cover section 6.1 of the chapter 6 of the Hibbeler book, and within these 4 lectures we cover chapter 6. So before I jump to talk about bending problem itself, I would like to remind you again of our big picture of Mechanics and Materials 1. What we want to do in this lecture is to find a relationship between deformations and loading for static problems. Now we learned how to calculate stresses from loadings in chapter 1. We learned how to calculate strains from deformations in chapter 2, and in chapter 3 we learned the relation between stresses and strains. Then in chapter 4, we talked about a particular type of problem, axial loading. In chapter 5, we talked about torsion. We had 4 lectures also on the topic torsion. Now, we will have 4 lectures on the topic bending. As you can see, both topics of torsion and bending, they are similar in a sense that they are dealing with a moment. So in these 2 problems, a moment is applied to a beam or to a shaft, in contrast to axial loading problem that the loading was a force. However, also bending and torsion are different in the sense that the directions of the moments are different. So in a torsion problem, the moment is basically along the same axis as the main axis, as the longitudinal axis of the shaft. But in a bending problem, this is orthogonal to that. So the moment M is called bending moment, in contrast to torque for a torsion problem. So usually when we want to talk about the topic bending, we are dealing with members that are deformed due to bending. And these members are usually beams, and for beams you can have different types of supports. For instance, you can imagine that you have a hinge here and then you have a roller on the right hand side. So this would be a simply supported beam. So basically you would get 2 interactions or 2 reaction forces on the left and 1 on the right. So there are 3 unknowns. And usually you have 3 equations. So it's a statically determinate problem. But you can also have a cantilevered beam where basically the support can give you axial force or horizontal force, vertical force, but also a moment. So now here you see again you have 3 unknowns and 3 equations. So that is also statically determined. Or you may have a similar scenario like the first one, but the roller may not be exactly at the end. In this case, we are talking about overhanging beams. In any case, any of these problems, they have 3 equations and 3 unknowns. And we are basically dealing with statically determined problems. So regardless of the nature of the supports on the beam, the bending problem is something like this. Usually you have a beam. On that beam, you have some sort of external loadings. It could be a concentrated force. It could be a distributed load. and the distributed load could have different types of distributions. Maybe it could be a constant, or it could be linear like it is shown here, or maybe something more complex. But in any case, the problem or the question here in the topic of bending is, what is the shear force distribution in the beam? What is the moment distribution in the beam as a function of x? And eventually, what is the deflection of the beam? So before we go to the topic deflection, we will need to answer these two questions. So we want to understand the shear force distribution and moment distribution in a beam. And that's all we want to do in chapter 6. We will come to the topic deflection in chapter 12 later. So in order to introduce the moments and shear forces in the beam and to better understand them, I begin with an example here. As you can imagine, bending, similar to torsion, is based on what you already know. So our main equations, our governing equations, are equilibrium equations. There is no new equation here. It's just rather understanding what we can do with the equations that we know. So the common equations are always, again, the sum of forces is 0 and the sum of moments is 0. These are our equilibrium equations, and this is everything we need to proceed with the topic bending. So in this example, you have a cantilevered beam with the length of 2 meters. You have a force of 5 Newton applied at the end, and it's downwards. And you're asked to calculate the shear force and moment at point C exactly in the middle. So we always start these problems as usual. We define a direction for external loads, or a positive direction or a positive convention for external loads. In this case, you have a force and a moment. And if you remember, we always said we usually take the upward direction for force to be positive and counterclockwise direction for moment to be positive. And this is, again, this is the external loading. Pay attention to that. So based on this convention, you can then draw the free body diagram and the reactions at the support. So from the support, you would have AY upwards and then MA in counterclockwise direction. So these are basically, or supposedly, these are the positive values. If we end up with a negative sign, we know that the directions that we have assumed here is wrong. So using our common equation, so the sum of forces in the y direction would be 0. You can clearly see that AY would be 5 Newton. And then sum of moments, for instance, with respect to, I don't know, B is 0. That clearly gives you that M at A is 10 Newton meter. And also it's coming with a plus sign, meaning that the counterclockwise direction that we assumed was correct. The same holds for both of them. They are both plus. Again, just pay attention that what I'm writing here is sum of moments with respect to point B, and this is the moment at A. All right, so now that you have those, what we want to do is to basically cut the beam at point C and calculate what are the internal loadings, what is the internal force, in this case a shear force, what is the internal moment, in this case a bending moment. So if we cut the beam at the point C, you can look at it from the right-hand side or left-hand side. On the right side, we have the section CB. On the left side, we have the section AC. Now, if you think of the shear force and moment at point C, looking at the right-hand side, you can imagine that due to equilibrium, you would need a shear force that is upwards, and you would need a moment 5 Newton meter that is counterclockwise. So you can see this as just a standalone system under equilibrium. But also you can look at the left-hand side. And now if you look at the left-hand side, you can see that the shear force at C must be downwards to balance the force at A, which is upwards. Or otherwise, you can just imagine that this 5 Newton is the reaction of the other 5 Newton that you have just next to it. Okay, so these two forces are basically internal forces. These are action reaction internal forces, and of course they should be always in equilibrium, so they should cancel each other. The same holds for moment. So you can imagine that now the moment at C should be clockwise, again 5 Newton meter, but now clockwise to keep this system in equilibrium, in static equilibrium. So as you can see from the picture, and we had a similar case, by the way, also for axial loading and for torsion, as you can see, the internal loadings are not easy to decide whether they are positive or negative, because you always have this action-reaction type of scenario. For external loadings, you don't have that problem. For external loadings, you have just the force, you decide about a direction, and then that's it. But here, if, for instance, if we assume that upwards is positive, then we cannot exactly say what is the shear force at C. Is it -5 or is it 5? It depends how you look at it. Are you looking from right or left? So for that matter, again, we need to define a new convention for internal forces and moments for a bending problem. So this would be our plus convention, or our positive convention for shear force and for bending moment. So we assume if you think of a piece of a beam or a cutout, on the right hand side, downward shear force is positive, and on the left hand side, upwards is positive. So if you look at it, it just feels that it wants to rotate this clockwise. So this would be the way to memorize it. So the plus direction for V would be such that it wants to turn that member clockwise. The plus direction for moment is such that it wants to bend the beam that holds water. So let's say if it's a bowl or something, it wants to bend it such that it holds water. Okay, so it's like that. So now using this convention for internal forces, which you should compare with the external ones, you can then define, or you can exactly prescribe whether the shear force and moment at C is positive or negative. So you can just confidently say, okay, the shear force at C is +5. The moment at C, the bending moment at C, is -5. And then again, once you say this, everybody knows what you mean, because -5 means that you would have a moment which is the opposite of what we have shown here, and +5 for the force, it shows that it's in the same direction, which is clearly exactly what you have here. So you can see on the right section, or let's say on the left section of the beam, which is the right end of it, you can see exactly now this holds. Okay? And then again, this would have been corresponding to this one. All right, so this is how we define the internal forces, but also now that we are having this, we can also define the shear force distribution, so internal force distribution. We just calculated it for a point C, for one point, but we can define it as a function of x. So the shear force as a function of x, as you can see, or as you can imagine from the picture, whether you cut it at C or any other point, the shear force would be always plus 5. And then again, plus means that it follows our convention. So the shear force would be a constant. But if you want to think of the moment is different. If you cut the beam at a section with distance x, the moment that you would get, again, at that point, you should draw the V and M, and you can write equilibrium equations. And if you write the equilibrium equations, you can see that the moment equation would be minus 10 plus 5x. Basically telling you that at point A, it would be minus 10. So pay attention that if you think of MA as an external moment, this is plus 10. So it's counterclockwise. But according to our scenario here, that would mean the minus 10. So it's minus 10 at A, which again means counterclockwise, by the way. And then it goes to 0 at B, and it goes linearly. Now, once you have the distribution through the length, you can pick your point C. So if the point C is in the middle, for instance, here, you can see that V would be, or the shear force would be plus 5, and the moment would be minus 5. All right. So the important message here is, again, similar to the discussion we had about axial loading and torsion. The important message here is to deal with internal loadings properly and to make sure that we are not making a mistake with the signs and with the values. And we can always calculate them from our equilibrium, from our static equilibrium equations. So if I want to summarize what we had for the conventions, this is for the internal loading conventions and this is for the external loading conventions. But now what happens to distributed loads? If we have distributed loads, the sign convention for external distributed force would be also positive if it is upwards, which is following obviously the usual convention that we have for external forces. So there is no surprise here. But importantly, I'm emphasizing on that because later we will see that the external loading relates to internal loading via this equation. And it's important that you remember that when we want to use this particular equation, if we want to say that externally distributed load W is V prime or dV over dx, this holds if we follow exactly this convention. So we have an equation here which relates internal and external loading, and we should be careful that we use the convention correctly. Okay, now that we know the sign convention and we know how to calculate shear forces and moment at a point inside the beam, we want to go to a next example. So in this example, you have a beam with the length of 4 meters under a distributed load 3 kilonewton per meter and it's uniformly distributed. And you are asked to draw the shear diagram and the moment diagram. So basically the distribution of shear force along the beam and the distribution of moment along the beam. So what we want to do is basically to cut the beam at the distance x from the support, in this case from the left support, and calculate the internal loadings. Before doing that though, maybe you should pay attention. What are the reactions at the supports? You can here see that the length is 4 meters and the distributed load is 3 kilonewton per meter. So the effective force would be 12 kilonewton exactly in the center, which requires 6 kilonewton on each support. So we can easily calculate the support reaction, and we will need it obviously for the following steps. So now that we want to proceed to calculate the internal loadings, we should pay attention that W here is downwards. So basically it's going to be a -3 according to our convention. Now, if you think about this piece and we draw the free body diagram, we have 6 kilonewton from the support, then we have the distributed load. Now, our convention for the force and moment is like that. So the moment is, again, because we cut it from the left-hand side, so the moment would be here counterclockwise, and the shear force is downwards. And these are the plus directions. Now, based on this, we want to write the equilibrium of forces. So equilibrium of forces is the sum of forces in the y direction is 0, assuming that upwards is positive. Now you can write that. So you would have +6 minus 3x. So again, 3 would be just the distributed load. So the effective force would be 3 times x at a distance x, applied in the center, obviously. So you would have +6 minus 3x minus v equals 0. And if you just reorder the terms, then you get the distribution of the shear force that would be 6 minus 3x. Next, we can calculate the moment distribution. For that, again, we draw now, or we replace the distributed force by the single force here, 3x, in the center. So that means it has the distance x over 2 from each side. And now, for instance, if you write the equilibrium of moments with respect to point C, you can see this is counterclockwise. Assuming that counterclockwise is plus, you would have plus m plus 3x times x over 2. So this would be the moment due to the force 3x, again with a plus. And the moment due to the force 6 kilonewton would be minus 6 times distance x. So it comes with a minus because it would cause a clockwise rotation, which would be negative. Now again, reordering this equation would give us the moment distribution in terms of x. That would be 6x minus 1.5 x squared. All right, now that we have the force distribution, the shear force distribution, and the moment distribution, all you need to do is to draw the diagrams. The shear force distribution is a linear function. It starts at 6. It has a slope -3. and it ends at -6. So it's basically this line, and in the middle, at the distance 2, the shear force would be 0. So this is shear force distribution. But also we have the equation for moment, so we can also draw the moment diagram. The moment diagram would be a polynomial of order 2, so it's a quadratic function. Now if you set x equals 0 here, you can clearly see moment is 0. If you set x equals 4 here, you can also see the moment would be 0. So if you insert x equals 4, you get 24 here, minus 1.5 times 16, which is also 24. So it's going to be 0, which is no surprise, by the way, because we know the supports cannot carry moments. So these are simple supports. So basically you get a quadratic function that is 0 at 0 and 4, and its maximum is at 2. Okay, so this is all for this example. But before I go to the next example, I want you to pay attention to two things here. The first thing is, pay attention that the maximum moment occurs where shear force is 0. So this may be a coincidence because this is the first example we are looking at this, but just remember that, and we will see that this is not a coincidence. Another point is, if you look at the functions that we have, at the distributions, the derivative of the moment function m prime is actually the shear force V. You can see it here. So if you differentiate m with respect to x, you can see that you get V. And more interestingly, if you differentiate V with respect to x, you get -3, which happens to be our distributed load omega, or W. Okay, so keep this in mind. As we will see, these are not just coincidences that happens in this particular example. These are universal equations that hold in bending problems, and we will see them happening again and again. And in the next lecture, basically, we will also prove them. So now the next example is very similar to the previous one, but in this case, we want to go one step more towards generalizing the idea. And by doing that, I mean, we want to replace the distributed load, which was 3 previously, we want to replace it by a value W itself. And then the length, which was 4 previously, it's now L. We want to solve this exact problem in a generalized manner with parameters. The process is exactly as we had before. So again, you cut the member, you draw the internal loadings according to our plus convention, and then again, our plus convention was this. So basically now we are cutting it such that this would be the right-hand side. Then you write the equilibrium equations. And then again, you can imagine if you have a force of W with the length L, the effective force would be WL. So on each support, you get WL divided by 2. And this is exactly the support reaction. And now in this system, if you want to calculate V, you would replace again the distributed load by a single force, this would be then W times X in the center. So from that, you can get Vx through equilibrium. And then also we can do the same thing for moment. So if you draw the moment, or if you want to calculate the moment from equilibrium of moments with respect to C, now you would have M with a plus sign. Then you have that force Wx times x over 2, but this will also cause a counterclockwise moment, so it comes with a plus, and then you get the moment due to the force WL over 2, so WL over 2 times x, it comes with a minus. You reorder the terms, and then you get the moment distribution in terms of x. And at this point, this is exactly what we had in the previous example. So you have now the force, the shear force distribution, and the moment distribution in terms of x. All you need to do is to draw them to get the shear diagram and the so-called moment diagram. As you can see here, when you set x equals 0, you get WL over 2, which is the reaction on the left. And if you set x equals L, you get WL over 2 with a minus sign, which basically is the minus reaction on the right. And then again, now the shear force distribution tells you that the shear force in the center at L over 2 is 0. If you calculate the moment, it's a similar story. If x is 0, you can see that moment is 0, which again is no surprise because it's a hinge. And then if you look at the right support, it's a roller support. So if x equals L, M is also 0. It's a quadratic function. And then again, we see that the maximum moment occurs where the shear force is 0. And also again, we see that even in this generalized form, these two relations hold. So M prime is indeed V and V prime is W. So in the next example, we want to just shortly discuss about the differences between these two cases. So imagine you have a beam with a distributed load W, and then you have the same beam with the same length, but now instead of a distributed load W, you have a single force, a concentrated force WL. So the equivalent of that force. Now, remember that WL is equivalent to the distributed force only in terms of being a force and in terms of calculating the support reactions. But when you calculate the shear forces and moments, these two systems are obviously not identical. So if you look at the left system, we just had it. This is the shear force distribution. But for the right system, you can imagine if I have a force here, WL over 2, and if I cut it here or here or here, at any point you cut it before you reach the center, you would get exactly the same shear force. So for the right system, the shear force distribution is different. It's constant until you come to the center, and then it just flips until the end of the beam. A similar story happens for the moment, obviously. So if you think of the left system, the moment is a quadratic function, and it has a maximum of WL squared divided by 8, which you can calculate it, obviously, by inserting it into the formula that we just had before. But if you think of the right system, now the moment would be a linear function, and its maximum would also be different. So it's just a function which increases from 0 to the middle. In that sense, it is similar, but that increase is linear. It's no longer quadratic like you had it before. And then again, you can see that here also, if you think of M prime, it's basically the same as V. So because V is constant, m would be a linear function, and here, because m is quadratic, v would be a linear function. Exercise 1 of this lecture is similar to problem 6.2 on page 263 of the book. You are given a beam here. It's a clamped beam or a cantilevered beam under a distributed load, a linearly distributed load, with its maximum being at W0, and you are asked to draw the shear diagram and the moment diagram. So basically, we want to find the shear force as a function of x and moment as a function of x, and then draw those diagrams. Now again, we start with the free body diagram and we calculate the reactions from the supports. In order to do that, we take the system, we replace the distributed load by its equivalent. So it starts from 0 to W0. The length is L. The area of the triangle, therefore, is 1/2 of W0 times L. So this is the effective force. And then its distance is L over 3 from the base, which is 2/3 of L from the left point. Now, once you replace the distributed load by a single force, you can write the equilibrium of forces, and then you would know at the support you get an upward force of W0 L over 2. And also then you write the equilibrium of moments. And for that, basically, you would need enough moment to cancel the moment due to the load. And basically, you would need a counterclockwise moment here, which is the distance 2/3 of L times W0 L over 2, and that would be W0 L squared divided by 3. Okay, so once you have the reactions from the support, you can now cut the member at the distance x, so somewhere here, and for that portion, you can also write equilibrium, and then from that equilibrium, you can calculate the shear force and moment. So again, if you cut it at distance x from the point, from the support, we draw the shear force and moment according to our convention. And all you have to do now is to write equilibrium for this system. That's what we want to do. So this is the system, and we want to write just the balance of forces and moments on this system. Now again, you have here a triangle. The slope of the line is W0 divided by L. So basically that tells you if you cut it at the distance x, the height of that triangle would be W0 divided by L times x. So this is the height of the triangle. The width would be, let's say, x, and then the area of that would be 1/2 of x times W0x over L. Okay, so this is the area of that triangle, which basically tells you that's your effective force. So if you want to replace that triangle but by a single force, this is your single force. Now the single force is again acting at the distance x over 3 from the right hand side and 2/3 of x from the left hand side. Okay, so now for this system, you have the forces and you have the moments, and all you have to do now is to calculate the shear force and moment from the equilibrium of forces and equilibrium of moments. Again, equilibrium of forces in this case is just equilibrium of forces in the y direction. Equilibrium of moments is just the equilibrium of moments, let's say, in the direction normal to the plane. Okay. Okay, so that's what we do. You write the equilibrium of forces in the y direction. Now W0 L divided by 2, it comes with a plus sign because it's upwards, and we assume upwards is positive. The equivalent force is downward, so it comes with a minus. And then the shear force is downwards, it comes with a minus. So if you reorder the terms, this would be the shear force function. So shear force V as a function of x is W0 divided by 2L, L squared minus x squared. Next, we write the balance of moments with respect to point C. Say this is point C, for instance. If you do that, now the moment here is counterclockwise, assuming that counterclockwise is plus. So you would have plus m the moment at the support is also counterclockwise. So you have also that plus W0 L squared divided by 3. The moment that you get due to the force at the support would be clockwise, so it would be the distance x times the force that comes with a minus. And the moment that you get due to the distributed load, it's the distance x divided by 3 times distributed load, and that would be counterclockwise, so that comes with a plus. So if you reorder the terms now for the moment equation, you also get the moment m as a function of x, and that's W0 divided by 6L times the expression in the parentheses. All right, so if we want to summarize everything, this is the beam, we have the reactions at the supports, and we have the functions for the shear force and for the moment in terms of x. So all you have to do now is to draw the diagrams. This is fairly simple. The shear force diagram, it's a second order polynomial, moment is a third order polynomial, but we can also see, for instance, that shear force at x0 would be W0 L over 2, which makes sense because that is exactly the reaction from the support. And then at the end, where x equals L, shear force is just 0, which also makes sense because we don't have additional force acting at the end. So that's that. And then you can also draw the moment. So for the moment diagram, again, you can set x equals 0. And if you set x equals 0, you get the moment to be minus W0 L squared divided by 3, which is basically the reaction from the support with a minus sign, admittedly, because we have a, let's say, for the internal convention, this would be clockwise. And then this was counterclockwise, so that's why you get a minus here. But in terms of value, it's the same thing. And also, if you set x equals L, then you also get 0 at the end of the beam. So that's that. This is all you were supposed to do for this example. But then again, before I go to the next example, I want you to pay attention to these two equations, or to these relations that they hold here. Again, you can see that if you differentiate m with respect to x, you get the shear force. And if you differentiate the shear force with respect to x, you get actually the W. So these relations, they hold again. And as I mentioned, in the following lectures, we are going to prove them and we are going to work with them differently. Exercise 2 and the last exercise of today's lecture is similar to problem 6.4 on page 265 of the book. Similar to the previous exercise, you are asked to draw the shear diagram and the moment diagram for the beam given in the figure. So you have a beam here. It's a simply supported beam. Here it's fixed at C and you have a roller at A. You have a distributed load, 5 kilonewton per meter. It's uniformly distributed. Then you have a single force, 15 kilonewton, and you have a moment at A, 80 kilonewton meters. The beam is 10 meters in total. So similar to the previous problems, we start with the free body diagrams. So from a free body diagram, we can calculate the reactions at A and C. So in order to do that, we can draw the reactions at A and C. These are, let's say, vertical reactions. Assuming that they are upwards, we can just draw them as such. The equivalent force of the 5 kilonewton per meter distributed load would be 25. So 5 times 5 is 25. Exactly in the middle of that portion, which means it's 2.5 meters from each side. So for the free body diagram here, you can write the equilibrium of forces in the x direction. You get AY plus CY, so they come with a plus sign, they are upwards, minus 15, because it's downwards, minus 5 times 5 or minus 25, it's 0. And then you write the equilibrium of moments with respect to point A. Again, point A is a roller support, so it does not apply a moment on its own, but you have an external moment applied to it. So the external moment here is not a reaction from the support, it's actually an external moment. Now, assuming that we take counterclockwise to be the plus direction, that moment, that external moment is minus 80. Then with respect to point A, the distance of the force 15 kilonewton is 5 meters, and it will cause a moment that is clockwise. So you get minus 15 times 5. Again, this is kilonewton meters, this is kilonewton and meter. So the units should be coherent and consistent. So that's that. And then from the 25 kilonewton force, you also get a moment that is clockwise, so it's negative, and the distance would be 7.5 meters. So you get minus 25 times 7.5. From the support C, you have the force Cy upwards, so you get a moment that is counterclockwise. So you get a plus sign, and the distance is 10 meters. Okay, now looking at these two equations, now you have two unknowns, Ay and Cy. So two equations, two unknowns. You can calculate the reactions from the support. At point A, the reaction is 5.75 kilonewton, and at point C, the reaction is 34.25 kilonewton. Okay, now that you have the reactions, you have everything for the beam to proceed and to calculate the internal forces or internal loadings, in this case, a shear force and moment. So you cut the beam at a point here, so between A and B, and then you can calculate V and M for this portion, but then for the portion from B to C, we cut it separately. So you can imagine, because you have a force, so you have a single force here, and then you have a distributed load, which does not come all the way to A, you can imagine you would have different distributions or different functions. For that matter, basically, we will split this into two parts. So in the first part, we call that coordinate x1, and x1 is from 0 to 5 meters. So it's basically from A to B. So from A to B, you write the equilibrium of forces in the y direction. You have the force at A, 5.75 kilonewton upwards, and V is downwards. So V would be 5.75 kilonewton. That's the shear force from A to B, and as you can imagine, it's a constant value. Now, if you want to calculate the moment between A to B, again, you cut it somewhere in between at the distance x1, and then you draw the moment according to our plus direction or plus convention. So you get plus m minus at, again assuming that counterclockwise is positive, minus 5.75 times x, because you can imagine that at the distance x, the force 5.75, it wants to cause a moment that is clockwise. So it comes with a minus, and this would give you your moment equation or moment distribution, and then again, the unit is kilonewton meters. Okay, so this is your shear force distribution, this is your moment distribution in terms of x. If x is between 0 and 5 meters, so maybe you should think of it as x1 to be more clear. So this is only valid if x is between 0 and 5. Now, we come to the second portion of the problem, and that is where x is between 5 and 10, and to be clear, we just call it x2. Now, in this portion, we are talking about cutting the beam somewhere here, or here, or here. It doesn't matter. Any point after point B. After point B, again, you have a shear force downwards. You have a moment. According to our convention, it's counterclockwise here. You would have a force 15 downwards. And then if you think, for instance, that you cut the beam at the distance x, the distance here is x minus 5. So the equivalent force that you get is 5 times x minus 5 or x2 minus 5. That would be the amount of force or the equivalent force of the distributed force, which is in the center of that rectangle, which again corresponds to x2 minus 5 divided by 2. So that's the distance. Now for this picture, you just treat it as a free body diagram, and for this picture you write also your equilibrium equations. Now again, assuming that the force in the y direction is positive upwards, you write 5.75 with a plus, minus 15, so that's the 15, minus 5 times x2 minus 5, that is basically this equivalent force, minus v is 0, and this equation gives you the shear force in terms of the coordinate x2 in kilonewton. Now you do it again for moment, assuming that counterclockwise is positive. So you can write the moment with respect to this point, for instance. Now you get m, which is plus, minus at, because it's clockwise, so minus. Now if you think of the force 5.75 with respect to this point, The distance is x2 and it will cause a clockwise moment, so you get minus 5.75 times x2. The force 15 is multiplied by the distance x2 minus 5, and that gives you a counterclockwise moment, so it comes with a plus. Now the equivalent force, 5 times x2 minus 5, should be multiplied by the distance x2 minus 5 divided by 2, and that would also cause a counterclockwise moment, so that comes with a plus sign, and then again this is also in kilonewton meters. All right, so if you just summarize everything that we have so far, we can calculate the moment and forces throughout the beam, and this is what we have. So if x is between 0 and 5, then this is your equations. These are your equations for shear force and moment, and then again maybe you want to think of it as x1. And if x is between 5 and 10, then these are your equations. So once we have these, we can also plot the diagrams. If you draw the diagrams according to the functions you have, you get these. So again, you can see that shear force is constant from A to B. Then you have a jump of that at point B. The jump would be exactly 15 kilonewton. So the distance, let's say from 5.75 to minus 9.25 would be exactly 15. And then that function would linearly decrease until you come to the point minus 34.25, which would be exactly the reaction at the support C. So that's your shear force diagram. Now your moment diagram is a linear distribution starting from 80, increasing because the slope of the line is positive, and then it will decrease quadratically according to this function until it comes to 0 at the end. Okay, so now you have the shear force diagram and moment diagram here. You can again check that the derivative of the moment diagram, or the derivative of moment, gives you the shear force. So m prime would be 5.75, which is exactly v. And then if you differentiate this with respect to x, you get 0, which is also okay because we know we don't have a distributed force here. So you can imagine that you have a distributed force of 0. In the second part, also the same holds. So m prime again. So if you differentiate this function with respect to x, you can see that here you get minus 5x2, and here you get your 15.75. So again, m prime is v, but also if you calculate now v prime, you get minus 5, which makes sense. This is your distributed load. Okay, that's it. So basically we have now the shear diagram and moment diagram for this fairly complicated load distribution on a beam. All right, this was our first lecture on the topic bending, and in this lecture we covered section 6.1. We have 4 lectures on this topic, and we will have 3 more lectures to come yet. And after that, we talk about deflections of the beam, which is chapter 12 of the Hibbeler book. I'll catch you in the next one.